Okay, the Hangout is live. So welcome again to another VJug session. Today's session is the async event-driven network application framework, Netty from Norman. Let me just share my screen first. Let's say hello to Norman. Hey, Norman, how you doing?
Pretty good. What about you?
Very good, thanks. And whereabouts are you calling in from today?
Well, I'm calling from Germany today, so near Frankfurt, in a small city.
Awesome, awesome, good to hear. Right, so let me quickly share my screen. This one, start screen share. Okay, so just a couple of things to go through before we start. Okay, so this is what we're talking about. You can follow Norman on Twitter. Norman works for Red Hat, and his Twitter handle is @Norman Maurer. I'll also paste that into the IRC chat as well. In terms of IRC, we're actually changing our channel from double hash or double pound virtual jug across to pound or hash virtual jug on Freenode. So exactly the same servers you're welcome to use, but we're on just a single hash now. So if you're in already and you're watching this, you can just type /join and then hash virtual jug. Well, on Twitter, we're @virtualjug, and we'll be tweeting a lot during this session. So please share or tweet us your feedback. Whoops, gone way too many. Okay, new site. I wanted to show you how far we've got on our new site. I wanted to be able to actually show this or do this session on our new site, but unfortunately we haven't got there quite yet. But what I can do is I can show you how far we have got and what you can expect to see in the future. So this, hopefully you can still see the screen. This is our new site. So from here you can scroll down and you'll be able to see the live session directly in our site. From here you can see IRC. I can say VJug Simon, and I can hit start, and I can log into my IRC within the same page as our video. So if I just say hello to people in here, hello VJuggers. And we've also got Twitter on the bottom so we can see what people are tweeting as well. So nice and interactive. There's our sponsors, Rebel Labs. You also, from this site, be able to see a whole bunch of past sessions. So all the sessions we have presented before, and this session will be up there shortly. Also a few bunch of stats. This is now up to 1,400 members, so that's really, really awesome. What's new on the Twitter feed as well? Future sessions. So here what we're looking to get is some meetup integration, whereby you can actually RSVP to sessions live on the site, and also add them to your calendar instantly, because as I well know today, I got some of the times a little bit messed up, so we can easily add it to our calendar, and that will add to your local time zone. A little bit about me and Oliver. The pictures need to be changed, and then a contact form. So yeah, we're really looking forward to starting this site. We need to do a bunch of performance testing first before we go live. And yeah, we'll hopefully have that session up or that site up for our next session. So let me just find my Google Hangouts and share my screen. So without further ado, then I'm going to hand you over to Norman, and Norman's going to tell you a little bit about Netty. Any questions, please add directly into the IRC, and that's again hash virtual jug rather than double hash. And I'll ask Norman periodically or at the end. So Norman, over to you.
Okay, thanks. So we'll just share my screen now and start. 1 sec. All right, everyone. So today I want to talk about Netty and why I think Netty is a pretty good thing to know and to use in your next project. So let's get started. Well, the first slide, as always, a little bit about me. My name is Norman Maurer. I'm working for Red Hat, and I'm leading the Netty efforts within Red Hat at the moment, which means they're basically take care about, make sure that things get into Netty that we need, that bugs get fixed and all that kind of things, and improvements get in, and also take care about the community. I'm also working on Vert.x, which is, well, an asynchronous platform based on Netty, and everything related to non-blocking I/O and also in performance. I'm writing a book at the moment, which is called Netty in Action, which is published by Manning. You can get the MEEP already. And then you also have this kind of information like, well, the Twitter handle and where you can follow me, and also the GitHub URL where you can just check out on which stuff I'm working on and all that kind of things. All right, so the agenda for today is basically, first off, what is Netty? Just, well, some introduction, some general stuff. A little bit about the features that Netty provides, about the buffers, which is basically the data container which is used by Netty, and also about the event loop and threading model in general. All right, okay, so what is Netty? Well, basically what we say at the website is Netty is a non-blocking I/O client-server framework, which allows you to quickly develop network applications and services. What quickly means here is basically we provide an easy-to-use API which hides most of the complex stuff from you, but still gives you a lot of flexibility. And we will see in the next slides what that means for you. Netty comes with a lot of features. I will go a little bit into more details about the features later in the slides, but for now, let me just give you, well, a raw overview about them. We have different transport services, which means the way how you send stuff over the wire and this kind of things. So basically, we support sockets and datagrams. Sockets here means about TCP and datagram UDP. We have some kind of HTTP tunneling transport, at least in 3 dot versions. We removed that because it's not needed anymore in 4 and in 5. We have some kind of in virtual machine pipe transport, which allows you to interact in the same Java virtual machine over the same API as you would do for TCP, for example. We have different kind of protocols. Now this list is increasing on every day or every week, so I've just highlighted a few of them which are mostly used, like HTTP, WebSockets. For WebSockets, we support, well, basically the latest draft and also earlier drafts. For client and server mode, we have support for SSL and TLS, star TLS. You just need to add a component in your configuration or in your pipeline, which I will talk more about later. And then it just works out of the box. You don't need to worry about SSL engine or something like that. We support Google protobufs for serialization, all kind of compression algorithm, have support for large file transfer out of the box, RTSP, and all kind of other protocols, which I will talk more about later. The whole core is built on some kind of event model, which means we have different kind of events that you can react on. Like, for example, there's some data which comes in and you need to handle this data. Or there was a new connection coming in and you want to handle that and this kind of stuff. We have a universal communication API, which means it doesn't matter if you use transport which use TCP or in virtual machine pipe. You always use the same API, so you just need to switch some classes, but the usage is still the same. And we also have our own byte buffer, which is, at least if you ask me, is a lot more feature-rich than byte buffer, which comes with the Java release itself. But we will look into this soon. So what about Netty? I mean, Netty is asynchronous, which means basically nothing blocks. You just get a future back and you can register a listener to that, or we have callbacks that get notified when something happens or something finished. We have this kind of unified API, which I just talked about. So whenever you use non-blocking I/O or whatever, you just use the same API. You can just switch it under it, and you don't need to change the code at all. It's pretty high performance. I mean, it's easy to say high performance, but I will show you some numbers later what that means. We have built-in buffer pooling to make allocating and deallocating buffers a lot faster. It's based on Cheb-Malloc algorithm. And we support gathering and scattering, which allows you to read into multiple buffers at once and also allows you to write multiple buffers at once, which means basically less syscalls. So I said asynchronous, but basically this just means no I/O operation will ever block. So what you do is basically to just trigger an operation, for example, a connect to a remote host, get back a future, and then the future you can register a listener, which is called general future listener, and this is notified once the operation completes. It can complete because of a success or of an error. If an error happens, you can retrieve this exception and can just do something with that. It really depends on the operation itself and also what you do exactly, if you can recover from the exception or not. So that's basically pretty generic. It really depends on your application logic. Then, because it's asynchronous and we don't block, we can share one thread for multiple connections, for example, which means you need a lot less resources to handle, for example, 10,000 connections. And it basically just works on this hollow principle, which means don't call us, we will call you once we are ready. So it's maybe a little bit different to what you use if you use blocking I/O. But you may ask, why should I care about non-blocking at all? I mean, blocking worked for me all the time in the past, but what you need to know is usually a thread takes about, well, 256 kilobytes to 1 megabyte for the stack space itself. So it's a lot of waste resource. You can tune that, but that's our default. So if you need a thread for every connection, even if your operation system can handle all that different threads and can do the context switching, all that kind of stuff in an efficient way, you still waste a lot of resources and memory that you could use for other things. So I would say it's always better to use less threads than use many threads. So transports. Now that you know a little bit about Netty, at least a high overview, let us go into transports at first, because we have a few different transport which all use the same unified API, which I said before. So you can just, well, remove one of the transports and exchange it with something else, and you don't need to change, at least your application logic, for example. So we have one which is based on non-blocking I/O itself, which is basically just an API on top of the Java NIO package stuff. Then we have a transport which is OIO, which we call old IO, which just wraps this old JavaNet stuff, but with the same API. We do some tricks there to, well, emulate this kind of behavior, what we have with other transports. Then we have a local transport. The local transport is this thing that I called NVM pipe before, which means you can just have these different channels, which are local channels, and you can talk with each other the same way like you would do, for example, if you talk over a socket like TCP. The API, all your logic is still the same. For example, Cassandra, the Cassandra guys or DataStack guys just published a blog post about that they switched to use Netty for their search stuff, and they use the local transport if they can query on the local machine itself, and just use the non-blocking I/O if they need to go over TCP. And they don't need to change anything for that. They can just exchange transport, and that's it. Then we have this embedded transport, which is a little bit different than other transports in this nature, that it basically allows you to talk with your channel handler implementation, which I'll show you later, which basically have all your application logic, your transformation logic, and can directly talk with them, for example, in unit tests. Or you can even use the Ambit channel to reuse some stuff in your own thing. But we see that later. And we now have the native transport, which is basically written in Java native interfaces directly using C, and used directly epoll edge triggered for the maximum performance and lowest latency. But I will also talk a little bit more about this, why we think it makes sense maybe. Then beside the transport itself, the implementation, we also have this kind of supported transport protocols. I call it like this. We support at the moment TCP. We have UDP, like datagram, multicasting, and all that kind of things. We have UDT, which is kind of, well, some, let me just call it like datagram for long distance. We have a serial support, so you can just use Netty with the same API to talk to a COM interface or something like that. And we also have SCTP now, but only on Linux, because that's the only one which is supported by Java itself at the moment. To make it pretty simple to use Netty, we have some state model. So once you have a new channel, which is basically the abstraction for the endpoint, the channel goes through different states where you can listen to for the state itself and react on them. So basically the first stage is channel registered. That means the channel was created, and we now register with an event loop. The event loop itself is responsible for dispatch the events that are for the channel itself. So it's basically just a thread which sits, for example, on non-blocking O on a selector and dispatch the stuff. Then after for example, for a socket connection or a socket channel, once it's connected, it goes over to the state channel active. And channel active means, well, we are now connected. So we can now start writing data or something like that. Then once we disconnect the channel, we close it, it goes to channel inactive, which means, well, the socket is closed, the remote peer is gone. And then after that, we go to channel unregistered, which means, well, we unregister the channel from the thread, and it will not fire any events anymore. It's now, well, it's not coupled to any thread anymore. It just releases all the resources and all that kind of things. One important thing is that once a channel was closed by you or by the remote peer, it cannot be reused. So you cannot reopen the channel itself. So basically, once it's closed, you need to create a new one to do another connection or something like that. Besides the states that I just showed you, which are basically the states that are triggered by Netty itself, you can also have a little bit of more complex states during the lifetime, because what we allow the user to deregister and re-register the channel itself, which means when a channel starts in the lifetime, first off, it gets registered on the event loop, like I said before, then it's active. So after you handle something, you don't want to do any I/O on the channel for some time, because, well, you just want to free up resources and you don't want it to process any events or whatever on the channel. So what you can do is you can unregister it with channel deregister from the event loop. Then you go the state to channel unregistered, and then you can re-register it again to the same event loop or even to another event loop, which also allows you to move channels from one event loop to another if maybe event loop gets too busy. And then the same goes away like before. It goes channel inactive, channel unregistered, and then it's over. But you can do the channel deregister and re-register and all that kind of things a few times if you like to. It may make sense. It's just a lot of more flexible than it would be otherwise. So let me talk a little bit about byte buff. So I said before, we use our own, well, kind of byte buffer. I will call it byte buffer on steroids, because when we start to use byte buffer, we was not satisfied with all the things that it offer out of the box, which makes things easier for our users. So what we did first was we now have separated indexes for reader and writer. So we have a reader index and also writer index, which makes it a lot easier to use than compared to byte buffer. Because for byte buffer, you need to flip the buffer or clear the buffer or compact it to switch the different modes, because otherwise, well, the index will not move to the correct position and you will not be able to write or read from to the buffer. Then we have implementations for direct and heap buffers, just like, well, byte buffer itself has two. But we also have a composite buffer. What's the composite buffer? Well, basically, what we do is we have a byte buffer implementation or an extended byte buffer implementation, which is called composite byte buffer, which allows you to wrap many byte buffs and still expose the same API like before. Because if you use byte buffer and want to do scattering or gathering, you need to pass an array of byte buffers to the API. So the API call is different compared to if you just do a normal read or write. But with Netty, with the composite byte buff, the API is still the same. It doesn't matter if it's, well, a composite of many byte buffs or if it's one byte buff or whatever. The API is still the same. You handle this the same way. You can read directly and whatever, and we do internally, well, choose the right byte buff to act on. And what we also have, they are resizable with the max capacity. What that basically means is if you use a byte buffer, which comes with Java itself, you allocate some chunk of memory, and then you can only write this amount of memory, and it doesn't expand if you try to write more. So it's a fixed size. What we do is more like what you see in an array list, for example. If you try to write more than the current capacity of the buffer, we just extend it to a maximum that you can specify. This allows you to not need to care too much about the bounds all the time. And what we also do is we have reference counting. Why we have this reference counting is pretty simple, because we have an allocator for byte buffs, which pool byte buffs for performance reasons. And because of the reference counting, we can make sure we know when we can release a byte buff itself, because otherwise we would need to depend on the garbage collector, which not work too good for direct byte buffers because we don't allocate out of the heap. But I will show you more about the allocator just in the next slides. So here I have some diagrams of our byte buff pool that we have. Basically, this was published at Twitter, at the Twitter engineering blog. They also use Netty. So whenever you use Twitter, you use Netty, which is pretty cool. So here we benchmark the different allocation times that are needed for different sizes of buffers and also for different types of buffers for unpooled and pooled. And if you look at the diagram, you see the performance or the impact of the pooling really goes with the size of the buffer. So if you try to allocate a pretty big buffer and it's not pooled, it's pretty slow compared to the time that it needs if it's pooled already. And it may surprise you a little bit that this is also true for heap buffers because they are living on the heap. But the reality or the truth is that also allocating heap buffers is not for free, because you need to zero out the array, or the Java virtual machine needs to zero out the byte array when you allocate, and that takes time. You can read more about that on the blog of Twitter. They Justin, one of my mates that worked with me on Netty, wrote that blog post, and you can see a lot of information about pooling and why it's important. It's just a little overview here. So I think now comes to the topics which are most important for the people. It's about channel handlers, because channel handlers allows you, well, to write your logic in some component, and also allows you to plug it in, remove it, and reuse it in some generic way, and also makes it easy to test. So what we have is, well, we have basically a channel handler, which is, well, the parent class or the parent interface of everything. And then we have a channel inbound handler, which has basically callbacks, which are called for inbound events. These are, for example, a new connection was made. There's some data to read and all that kind of things. And then we have the channel inbound handler adapter, which basically just implements all the methods of the interface and allows you to just override them that you're interested in. And we have the same for outbound. So we have a channel outbound handler, which is basically just called when you say, I want to write this data to the remote viewer, for example, or I want to do this connection. And then we also have this adapter class, which just implements everything, and you can just override it. Makes it a little bit more easy to use. And what is interesting about the channel handler is that it's called by the assigned event executor, which is basically, as default, the event loop itself. So basically, everything is handled by the same thread for this channel. We will see a little bit more about that in later slides. So what you basically use these channel handlers for? Well, basically, it's for convert data. Like here you have bytes, and I want to make a poacher out of that, for example. For your business logic, like, well, now I have this poacher, which I want to handle, and I want to write it in the log file or whatever, or do something with that. Or also react on state changes, like, well, I have just a new connection coming in. I want to proxy this connection to other host, or lock it, or whatever, or reject it. Here you see the channel inbound handler interface itself, all the methods. I would just go, well, quickly through the methods so we get a better idea when they are called. Well, I think general registered, general unregistered, it's pretty clear. It's when it's registered to the event loop, the channel. Then channel active is when it gets active, like it's connected. Inactive when it's closed, for example. Channel read is called when there was something read from the wire, from the socket, and it's dispatched through the pipeline to the channel handlers. Channel read complete is a little bit of a special one. This one is triggered once we was not able to read another pack of data from the socket. And then we have user event triggered, which allows you to also trigger your own custom events and react on them. Then we have channel writability changed, which means basically, well, I try to write to the channel, but the socket or the network stack was overwhelmed, and I was not able to write everything out yet. So I need to back up, some kind of back pressure, and write the rest once the network stack is, for example, writable again. And then also exception caught, which is basically just called if some exception is thrown when you process stuff. And all of these inbound methods are basically triggered by Netty itself when it reads stuff from the channel or accept new connections and all that kind of things. Yeah, like I said before, we also have this channel outbound handler. There's a little bit different. We have different kind of methods and callbacks which are called when you trigger some operation on the channel itself. These are usually triggered by the user, like I want to bind the channel. Then this bind callback is executed, and you can intercept it, you can block it, whatever. You can redirect it, whatever you want. And maybe you notice you also get a channel promise as an argument of the methods, which allows you to add, for example, a listener to that, which is notified once the operation completes, or also allows you to fail the operation directly by, say, promise, set failure, and set an exception on that. Yeah, and we also have this for connect. If someone tries to connect to a remote host, disconnect if you want to disconnect, close if you want to close the channel, deregister, which is called once some channel will be deregistered from event loop. Then we have read, which basically is triggered. You can use Netty in two different modes. You can use auto read mode, which is basically the default, which means Netty tries to read always from the socket, from the channel itself, from the socket when something is there, and then it dispatches it. Or you can also say, well, I want to disable auto read and want to trigger general.read every time I want to read something from the socket. And this method is called in this case. Then we have write, which means, well, something should be written, which is one difference or one special thing about Netty is we have write and flush. So why we have this? So write basically means we want to write it through all the handlers to the end and queue it in the channel itself. It's not written to the socket yet. Once you call flush, everything is, we try to write everything which was written before. It's kind of, if you use a buffered output stream, for example. This allows to do kind of pipelining pretty easy. So for example, if you use HTTP, which allows to pipeline, you can use write to write all the requests to the end. And then after you, for example, have 10 writes done, you say, now flush all. And you can maybe flush all with one syscall, which is much faster than do a syscall for every write. That's basically why we have flush and write split up. One thing which is kind of new in Netty 4 compared to Netty 3, if you know Netty 3, what we did there was basically the API itself. What we did was we fired a new object event, which was basically just an object and fired it through the pipeline to all the channel handlers. The thing is, that was pretty bad in terms of garbage collector pressure at the end. So because if you push things hard enough, you create one extra object per event. And that can be pretty bad if you write a lot of data or receive a lot of data or this kind of thing. So what we did in Netty 4 and Netty 5 also for sure was we removed this old API decision, and that was one of the cases why the API changed completely, and replaced this event thing, like only have one method and have different kind of events, with one special method signature per event. Because now we are able to say, well, call directly this method and it just flows through the pipeline. We don't have this extra object that we need to allocate, and also this doesn't need to get garbage collected.
Got a quick question.
Yes.
If we actually go two slides back, actually.
Okay, let me just move back. This one, right?
The API.
Yeah.
Interesting question, actually. This is probably more of a discussion than than having one true answer. But it'll be interesting to hear your opinion. This is from Ivan RSC. All methods in this API throw a root exception. Is there any reason you didn't choose to create a new Netty exception or anything like that?
Basically, we didn't do that because, first off, basically in this handlers, in this implementation, they left the code of the user, and it may throw any exception. We don't know which exception. And if we would say, well, it needs to throw a Netty exception, we just produce overhead because you need to, well, rethrow the exception. I mean, you need to wrap it again and then rethrow it. And we don't gain everything of that. I mean, it doesn't matter for us if it's our own exception or exception itself, which is thrown because of a user error or whatever. So that was basically why we used exception. It doesn't make any difference to us.
Okay, perfect. So that makes sense. So it's for
I mean, every exception that is handled in Netty doesn't, well, bubble up to the user outside of the Netty framework, because it just gets dispatched to exception court, for example, or it gets dispatched to the channel promise and favorite channel promise. So it doesn't make sense to have some special exception type.
Cool. Thank you, Norman.
Anything else, or should I just go?
Let's continue. There are a couple of other questions, but they're not relevant to particular slides. They're more general questions, so I'll ask at the end.
Okay, perfect. Okay, let me see. It was here. Okay, so yeah, that was basically why we did this kind of new API where we just have methods and call that again. So I talked a little bit about channel handlers. Now let us see what you can do, for example, with that. It's just a really basic example. If you're interested in more, well, more complete examples or more complex, we have a whole example tree in our GitHub repository where you can see a lot of things. But I just did a little bit which shows something, and you can guess what is going on. It's not too big, so it fits on the slide. So basically, we have this echo handler, which extends general inbound handler adapter, which is just, well, the adapter class, which I was talking about before, which allows you to just override the method that you're interested in. So what we do is we override the general read method, which is called every time we receive some data that it's read. So what we do here is we get passed in a channel handler context. The channel handler context itself is unique to the handler and the pipeline where the handler sits in. We will talk about pipelines in the next slide, I think. And then we get the message itself, which is object. So you may ask yourself why it's object. It's basically because we don't know exactly what the object is like. Because I mean, if it's a TCP socket, for example, the message itself is a byte buff when it gets dispatched from the socket. But then you may change it, decode it to something else, and it may be a string after that. So we need to take everything. And also, for example, if you use datagram, it's not a byte buff, it's a datagram packet, because we also have the remote address, local address, and all that kind of things in the packet itself. So yeah, the channel read method is called, and then we call write and flush on the channel handler context, which basically means just write it through the pipeline to the end in the socket queue, and then flush it out directly. So we just echo the stuff back to the remote peer. And then we also override the exception code, which is triggered once an error happens, and print out the stack trace. Well, you could do locking. Maybe you could recover from the exception or from the cause itself. If you say, well, if it's instance of my exception, I can roll back a transaction or whatever. And then we close the channel itself, which means where we basically lose a connection or something like that. We don't do this closing by default for exception code because it really depends on the application logic and the protocol what you want to do. That's basically it. And what we also have here, we have this annotation which is called shareable, which basically means this same instance has no state, so you can use the same instance for different channels, for different connections, and don't need to create a new one. So before you basically or most often add your own channel handler, you need to get this byte buff, which is, for example, dispatched from the socket itself and convert it to some poacher or something else to handle with, because you don't want to act directly on the byte buff in the application logic. So for this, you basically have an encoder or decoder, which is just an implementation of an inbound or outbound handler at the end. We ship a lot of decoders, encoders out of the box. There are too many to fit it on the slides, but I would just highlight the most interesting, most used at the moment. Basically, what we support is we have an HTTP codec, which basically takes a byte buff and transforms this byte buff to a series of poachers, like HTTP request, which contains all the headers, everything parsed. And then we have HTTP contents, which are just chunks of data. So we don't buffer the whole HTTP request, for example. We dispatch it like we read it from the socket. This allows you to do streaming and all that kind of things without need too much memory. We just lately get a pull request for HTTP2, which was submitted by some guys from Google itself. And this is currently work in progress, basically because HTTP2 is still not final yet. It's we just have an open pull request at the moment, which implements Trev 12, which will be merged maybe today or tomorrow, depends a little bit. But until this, it's still work in progress, but you can check it out already. We have WebSocket support for client server, whatever, all the major versions. Speedy. Basically, we ship Speedy 3.1, the latest draft at the moment. This codec is also used by Twitter and was also contributed by Twitter. We have support for SSL, TLS. You just add a channel handler implementation to your pipeline and everything is encrypted out of the box. Serialization, where we ship different things like, well, stock JDK serialization, JBoss measuring, and all that kind of things. And we also support gsip, deflate, and all that kind of stuff.
Norman, any plans for SBE support in the future?
SBE, well, basically we don't have any plans yet. But I mean, it's open source. We will accept pull requests. If anyone will write one, we will happily review and pull in. So basically, well, it's what we basically, or most of the times, do is just, well, we have protocols and then we get pull requests for other protocols, and if they match our expectations and we say, well, that's generic useful, we just pull it in, just like that. So if anyone writes SBE support, I'm happy to review and pull it in.
Awesome, thanks.
Okay, so like I said, I mean, the decoder is basically just an inbound handler, but because of the non-blocking nature, we try to make it easier for the user to write these, because you don't know, you cannot block until enough data is there. I mean, you need to get notified once more data is there and check if it's enough. If not, notify me again if more is there and all that kind of thing. So what we have a byte to message decoder, abstract base class, which you can just extend, and this handles all this all the buffering for you out of the box. So what you don't read from the byte buff itself and add to the out list will stay there, and you can read again in the next event from it. And we also make sure that this byte, the buffering, or the buffer itself, which is used for this buffering, gets released once the channel is disconnected, for example. And then we also have this message-to-message decoder, which just allowed for POCHO-to-POCHO decoding. Like, well, I have my POCHO here, and I want to convert it to a string, and that's it. And this different kind of, well, decoders makes it pretty flexible to write your own application logic and make it pretty easy to reuse. For example, you can have a HTTP decoder and can use it everywhere where you want to support HTTP. And then you can have a string decoder where you can put it in everywhere where you want to decode from HTTP to string and this kind of stuff. And then we have the same for outbound, for encoders, for encode stuff. So what we have is we have an abstract class to convert from POCHO to bytes, which just, well, gets cold, and then it dispatches. And we also have the same for POCHOs again. It's basically the same like, well, like for inbound or decoding. It's just one is coming in and one is going out. We also have other generic useful decoders, which, well, I want to mention because they are often used. We have a replay decoder, which tries to make it easier for the user to do, well, to work with this non-blocking stuff where he needs to check normally if enough data is there to read. So what we have here is, well, the replay decoder is kind of a byte-to-message decoder, but what we do there is we wrap this byte buff, which come from the socket, with another implementation, and once you try to read behind the data which is ready to read, we throw a special signal and catch it again in our decoder and rewind all the indexes to a last checkpoint that was set, and well, get dispatched again when the event is there. So you don't need to check every time, well, I want to read along, are there 8 bytes ready to read and all that kind of things. Then we have this fixed length frame decoder, which is basically just, well, you can say, I know all my frames are 512 bytes long. So you give a constructor argument like 512 bytes, and then it cuts the frames at this size and dispatch only frames which are at this side to the next handlers in the pipeline. Then we have a length file-based frame decoder, which allows you to do something like, I know I have this protocol, and on this position in the header of the protocol, which are in the byte buff, there is a long file, for example, which holds the actually size of the payload or the length of the payload, and cut me out frames which match this. It's pretty flexible. For example, MySQL, PostgreSQL, MongoDB, and all that kind of things use this kind of protocol. Then we have a line-based frame decoder, which is optimized to split frames or byte buffs on the carriage return, for example. And we also have a delimiter-based frame decoder, which allows you to say, well, I have this delimiter like a tab, and I want to cut frames out on tabs, for example. So now you know about channel handlers, but how you assemble them or stick them together. For this, we have this abstraction, which is called a channel pipeline. So what is a channel pipeline? Basically, it's just a double linked list which holds different channel handlers. It's per channel, so a channel pipeline is created per channel and is assigned to it and stick on that. All the events flow through the channel pipeline and through the handler that are located in it. And it allows on-the-fly modification, so you can write kind of multiplexing stuff. We use this kind of feature, for example, to upgrade from HTTP to WebSockets. So what we do is we just move out the HTTP decoder, encoder from the pipeline and stick in the WebSockets decoder, encoder once we detect an upgrade. So just think of it like a Unix pipeline. So you can just usher something in, have a pipe, do something else with that, and you get an output. And this is how it works, basically. So you see you have the channel pipeline, then you have inbound handlers, which are at the bottom, and we have inbound events. And this flow from the beginning, that we call the head of the pipeline, through the tail. And then we have outbound events, which are, for example, channel write, channel connect, and all that kind of things. And this flow in the other direction, from the tail to the outbound, from the tail to the head. And this is how it looks, how you configure channel pipeline actually. So you have a channel, a reference, you get the pipeline from it, and then you can do different things. So first off, at point one, what we do is we just add a new protocol codec, which is just an implementation of channel handler. And this one is executed by the event loop itself, which is the thread which does all the I/O for the channel itself, which is good enough for most of the use cases. But then there may be situations where you need to block, and you don't want to block the event loop because when you do that, you block everything that sits on the same event loop, which may be many channels, because we want to share resources. So what we allow to do is we allow to create a called event executor, which is basically just a special thread pool. And what we allow to do is we say you can add this channel handler and assign it to an event executor, which we give also as an argument. And every event, every method that is called for this handler is called by this thread. So we just dispatch it away from the event loop, dispatch it on the event executor itself, and then execute your logic in. And then you can also do that and create another one, and can use another one for other handlers. So you can really separate it like for different stages of this kind of things. You can even go back and say, okay, now I executed 2 handlers with extra event executors, and now I want to move back on the event loop itself, and this works. It will just dispatch it internally, and you don't need to worry about that. So the event loop. The event loop itself does the heavy work or the heavy lifting in Netty. The event loop is just basically a thread which dispatches event in a loop. That's why it's called event loop. For example, Node.js is pretty famous for this kind of working, and the same is also used in Netty itself. So what we have an event loop, or we may have many event loops. One event loop is also one thread. It powers 0 to many channels. It really depends. And it's exactly bound to one thread. So everything that is handled by event loop is always executed only by one thread. And well, that means you basically don't need to worry about synchronization at all, because everything is just dispatched by the same thread. Everything is visible. You don't need to have any concurrent stuff going on there by yourself. The only thing when you really need to worry about this is if you have a handler that you share across different channels, because these channels maybe sit on different event loops. But most of the times you don't need that. And this is basically how this looks like. You have an event loop group, which we call like this. It's basically just a group of event loops. So you say, well, I have an event loop group and I have 3 event loops in there. And every time a new channel is registered, I will just use one of the event loops out of this group and stick it on that. And it will stay there. And at the moment, we use some kind of round robin algorithm to choose which event loop we want to stick the channel on. But this will change. I mean, we will still have round robin by default, but we have now Google Sum of Code, and we have some student which works on some kind of different strategies. So you will be able to plug in your own strategy, which will get some metrics back, like, for example, how long did it take for the event loop to process all the events, or how many channels are sitting on the event loop, and this kind of things, because this allows you to detect which event loop is, well, the one which has enough resources or most resources out of all of my event loops. This is especially important if you have long-living connections or different kind of connections which can get out of balance. And also one nice thing about the event loop itself is it extends a schedule executor service. So that means you basically get all the goodies for free that schedule executor service itself provides. This means you are able to schedule new tasks on the event loop or on the event executor itself. And this task will get executed by the same thread, because it's the same event loop, than the other I/O operations do. And this means you don't need to synchronize, which is pretty neat. The only downside of this is that when you schedule something for maybe run in 30 seconds, we may not be able to run it exactly in 30 seconds because something is just handled on the I/O, on the event loop because of I/O. So it may be run in 31 seconds. But most of the times it's not so important to have it, really so much, correct. It doesn't matter if it's 1 second later or something like that. If you need this, you can still use a normal schedule executor service, which is come with the JDK, but then you need to worry about synchronization again. And here you see an example what you can do with it. You can do a lot of other things, but this is one of the things that we saw in the usage. You have this write method, which is basically just invoked when something should be written, and then you use the promise and check if it's done. If it's not done yet, which this means it's not written, and then you schedule a task which can, for example, check if it's written in 30 seconds, and if not, we would just close the connections because we say, well, we cannot handle it, something like that. Or you could also do some kind of auto flush where you say, I want to flush all the data every 30 seconds or something like that. You also need a way to bootstrap your application in an easy way. And for this, we have different kind of bootstraps. We have fluent API like a DSL to do this. I would show you that in the next slides. It supports Graceful Shutdown, which means basically, well, we have this event loop group, and it has n event loops, and we handle events there. And we don't want to just, well, stop processing, because then we may interrupt connections pretty heavy and all that kind of thing. So Graceful Shutdown means you can do something like, well, try for the next 5 seconds and check if there was 1 second with no I/O operation going on, and if this is the case, shut it down. And if you was not able in 5 seconds, then you need to, well, hard shut it down. It's more like a graceful thing going on. And it allows for a unified way to start up. So it's basically the same if you use NIO, OIO, or whatever. You will see it now. So we have the server Bootstrap. This is how you bootstrap a server, which will accept connections like TCP or something like that. So you first create a server Bootstrap instance, and then also event loop group, which has these event loops sitting there that handle the events. We have different event loop group implementations for the different transport implementations. We have NIO event loop group, OIO event loop group, and all that kind of things. Then you say, well, use this group, and group takes 2 arguments here, because we allow to use different groups for accepting new connections and for handling the I/O for the accepted connections. Why we do that? Well, it allows you to say, well, use this group to accept, and I don't want to be impacted if the other group is too busy handling all the I/O from the already accepted things. So you don't get any connection timeouts, for example. Then you set the channel itself, which will be used in implementation. Then you say, well, we want to bind to this local address. We want to have this child handler. The child handler is invoked for every accepted new channel. And there you basically set up the pipeline itself, where you add all your handlers like, well, I want to have it encrypted, use the SSL handler. I want to have HTTP decoder, put the HTTP decoder in, all that kind of things. And then at last you use a bind, which means, well, we bind to a socket now, to address, and now we accept stuff. And what I'm doing here is I call sync, which means block until the bind was successful, or not successful, until the bind was completed. If you have a full asynchronous startup method or whatever, you also could not use sync, but register channel future listener to the return future itself and get notified when the bind is complete. For example, Vert.x use something like that. And then what I'm doing here is I get the close future of the channel and do a sync on that, which just means we block until the server channel itself, which is bound, is closed. And then in the final block, I do the shutdown gracefully, which just means, well, try to gracefully shut down all the threads, all the event loops, and all that kind of things. Then we have Bootstrap, which looks pretty similar. The Bootstrap itself is in this kind different to server Bootstrap, that it's used for channel implementations which don't accept other channels, which just handle stuff by themselves. One example is the new socket channel, which is just used for a TCP client, but also a datagram channel, which would be this kind of thing. And there you also get a remote address where you say, well, I want to connect to this address. Then you set the handler itself. The handler is, again, it's called to set up the pipeline once the channel is registered. And then you do the connect thing, which just means, well, connect to the remote peers. So it's kind of the same like before, just with connect and not bind. What we just introduced now in Netty 4, I think it was first coming in Netty 4, 4.0.16 or 17, is we have now a native transport. I said it before, but let me get you a little bit more details why we did this. First off, APOL has different modes, which allows to use level triggered and edge triggered. And the implementation, which is used in Java JDK, is level triggered. It's like this because, well, it makes it easier to provide a unified API for different operation systems, for how you can interact with the JDK channels. But for Netty itself, edge triggered is most of the times a better fit, because for the model, for the state model, event model that we use in Netty, what we want to do is we want to get notified once there's some change, once there's some state change or data is there or something like that. And then we want to dispatch it right away. And this is what edge triggered is all about. You only get notified once about an event, and you need to handle it. And that's why we use edge triggered. Then we support different TCP and socket options, which are only exist on Linux and also some BSDs, but we only support Linux at the moment, which is, for example, TCP Cork, which allows you to pretty efficient write a buffer and also the content of a file with one network package, for example, TCP package. And we also support SO reuse address, which allows you to bind multiple sockets to the same address. You may ask yourself why you want to do that. Well, it's pretty easy. If you need to handle a lot of connections, like accepting them, you may not be able to accept fast enough. So connections get dropped. But if you are able to bind to the same address with multiple channels, you can also have multiple threads. And this allows you to accept a lot faster. That's especially useful for Datacram UDP. There's some post, some presentation of some Google engineer where he talks about the impact of this option and how it impacts, for example, a DNS server. And at the moment, we support TCP and UDP. And yeah, it can be used on Linux for maximum performance. It's still pretty young, but Google is using it already. So I think, yeah, it will only improve in the future. So what things we have to come? We want to support dynamic general register. Why we want to do that? This is because if you have a lot of channels that are connected and handled and put on the event loop, they may get out of balance. How busy some channels are. Maybe some are handling pretty heavy traffic, some others don't see anything. There it would be really interesting to be able to say, okay, well, this event loop is pretty utilized. Take X channels out of this and re-register it with another event loop which is not so busy to better utilize the resources. This is one of the tasks some student is working on for Google Summer of Code. And related to this, we are thinking about writing a new event loop implementation which using the fork join pool under the hood, because this allows it easier to do this re-register stuff. Then we will ship an open SSL-based SSL engine because it's in our tests, it's faster with handshaking, all that kind of things. We already have an open pull request for this one, which is just pending because of review stuff, and this will be included in the next release. And also, Twitter is using that already. It was part of Finagle native, but it's merged to Netty now. And we also want to support metrics, so like getting some metrics back, how busy an event loop is, how many channels are registered, how many bytes are written, how many failures, and whatever. So this kind of stuff, and expose it on some kind of callbacks where you can plug in, for example, JMX or whatever you want to do. Yeah, and now we are, well, basically mostly at the end, and I just want to give you an overview about companies that are using Netty. Well, of course, Reddit is using it because, well, I guess otherwise it would not work for Reddit. Facebook is using it. Maybe let me just say a little bit how they use it. Red Hat is using it for InfiniSpan, Hornet Queue, and other things. So in our products also. Facebook is using it. They have written their own thrift server on top of Netty, which is called Nifty. It's open source also. Cisco is using it. I don't know exactly what the service does because it's not open source, but they also opened up some issues and all that kind of things. Firebase is using it for their API, their push stuff. Twitter is using it basically in Finagle, which is built on top of Netty. So it's, well, the heart of their whole service stack. DataStax, like I said before, they're using that for their search stuff. Netflix, they just open sourced a project which is called RX Netty, which allows you to write, well, Netty services in a fluent way. Urban Airship, LinkedIn is using it, and also, well, Google is using it in Open Bidder project about ads. And there they use also this native transport where what I talked more about that. Yeah, and then I also have kind of a project overview about projects that are using Netty. There are a lot of more of them. We have a lot of other projects on the website. You can check it out there, and also other companies, but I just want to highlight a few. Vert.x is using Netty for its core. Cassandra use Netty for their SQL driver, SQL client. InfiniSpan is using it for hot rod protocol and memcached. Finagle is using it for all that stuff that they expose. Storm now has a transport based on Netty. Hornet Queue for all the JMS stuff. The Play framework, using it for HTTP and WebSockets and whatever. Reactor, use it for their TCP stack. Minecraft is using Netty now. Eclipse can I say? Elasticsearch is using it for their APIs, and also Redpack and many more. Just, well, if you're more interested in that, go on the website and check it out there. And yeah, like I said, I mean, we love contributions. So whenever you think you can contribute something, and it doesn't matter how big it is. I mean, it can even be comments on the documentation. We love pull requests and documentation because, you know, documentation writing is always a little bit, yeah, it's hard work. Feedback, bug reports, pull requests, features, whatever. We really love contributions, and because of that, we really want you. Yeah, and here are the list how you get involved. I mean, you have mailing list, IRC channel, a website, an issue tracker, also Stack Overflow. You can post questions there, and we will just answer them. Yeah, and now a shameless self-plug. I mean, buy my book if you're interested. Make me rich. Maybe I can retire soon. And yeah, I mean, basically that's it. Here now the references for the websites. The slides are generated by ASCII Doctor, which is a pretty amazing project, and DC Slides. The templates are done by Dan Allen, Sarah White, and all the pictures and all that stuff is licensed under Creative Commons Attribution. And so. Okay, that's it basically. So now I'm open for questions.
Awesome, thank you very, very much, Norman. That was awesome. I'm going to ask a couple of questions. We're running low on time, so I'll ask a couple of questions and then we can continue in IRC. One question, I'm going to actually go straight to Ivan again. One question which you can really only ask on something like the VJug, just because we're effectively going to go to someone else's slides. I'm just going to share my screen very briefly. Share this one. So on my screen now, you should be able to see a throughput of between a regular I/O server and an I/O server. The question is, would you say that these benchmarks from Paul Timer are obsolete now with Netty? the myth that he was trying to break was that Java asynchronous Neo has a higher output than Java IO. So let me show you the screen again.
Well, basically, I mean, the thing is that with non-blocking I/O, you pay some kind of price with latency a little bit, because you need to get, well, this event and all that kind of things and dispatch. And so so if you only have one connection, I mean, you only need to handle one connection, for example. It's true that blocking I/O has often a better throughput than non-blocking I/O. That's true. But as soon as you need to handle a lot of concurrent connections, and this is where non-blocking I/O really shines. I mean, we are talking about having 10,000 of connections concurrently handled. Then non-blocking I/O gives you a lot of better resource utilization than I/O or blocking I/O. So, I mean, it really depends on the use case. So, if you only have one connection, for example, and you have all the way down blocking APIs, you may be better off use blocking I/O, because you need to block anyway at some point. But if you have only asynchronous APIs and need to handle a lot of stuff, then non-blocking I/O will outperform blocking I/O for sure.
Okay, cool. One other question from Mercurus, I hope I said that right, and also one from Mike Mitreski, who wanted to ask the same thing, was about Java 8 support. Presumably you can use Java 8 lambdas with Netty without any problem.
Yeah, basically, I mean, you can use, for some stuff you already can use lambdas, because, well, we have some interfaces like channel future listener which only have one method, which is a perfect fit for that. But for the callbacks itself, like channel inbound handler or channel outbound handler, you can't do that, because well, we have many methods in there. But we may include adapters pretty soon, so you can have some kind of adapters to wrap in Lambda and just, well, get it called for the right event, for example. But for Netty 4, we what we need, or what we do is we require Java 6. Some features are only ready to use if you have Java 7, like, for example, datagram multicast support for non-blocking I/O, because that was only introduced in Java 7. And we can't depend on Java 8 yet. I mean, I think it's just too early for this kind of generic framework to have the users required to use Java 8 in production. And I don't think we will depend on Java 8 pretty soon. It may be optional, like, well, you can use it. We may have a module which provides some goodies for Java 8, but it's not in the core itself. It's not required. We have this for other features, for example. I mean, our own core of Netty has 0 dependencies. We have 0 dependencies itself. But if you want to use some features, like you want to use the encoders and decoders for Google protobuffs, for example, you need to include this jar, and this has optional dependencies on Google protobuffs. Because otherwise, well, we would need to rewrite everything from scratch, which doesn't make any sense. Mm-hmm. But the core itself has 0 dependencies. Yeah.
Okay, awesome. And one last question that I'll finish up with from Robert P. Asking about if it's possible to close the connection or get an error when you do receive an amount of data, but the complete message hasn't been delivered after a certain time. So, for example, shutting down the connection if after, say, 10 seconds you haven't received the full message.
Yeah, I mean, what we have, for example, for exactly this kind of use cases, we have which is called an idle state handler, which allows to configure different idle states. So you can say, for example, if there was nothing read from the channel for the last 10 seconds, we will fire an event, and you can react on the event. Like, you can close the channel, or you can send, well, a heartbeat to get notified if the channel is not there, because then you get an error. And you can also have different timeouts for writes, or for if no writes and no reads are done in the last time unit, whatever, you get another event, and can you react on that? That's basically, most of the times it's used, for example, for heartbeats. So you can move in that handler and can say, well, if nothing was written for 10 seconds, send automatically, for example, in WebSockets, a ping frame, just to make sure that stuff stays alive. Yeah. And this is one of the cool things about Netty. It's so generic that we can write it once, and you can use it everywhere where you need this functionality.
Awesome. Okay, so there are a few more questions in IRC, but we should wrap up. So I'll just finish by saying thank you very much to Norman for spending the time and being part of the VJug. If you have any feedback, let me share my screen again. If you have any feedback, feel free to ping Norman. His is, hope you can see my screen now. Norman Maurer is at Norman Maurer on Twitter. If you have any feedback around the VJug specifically, you can grab me at sjmaple on Twitter. Our next session is still to be decided in terms of the date and time and the title. It's going to be on class loaders by request. There were a few requests about understanding class loaders in a little bit more depth. And Zero Turnaround actually do a really good class loader session. So we're going to run that session, and that's going to be run by Anton Arapov, who is the JRebel architect or product lead in Zero Turnaround. So we've had all our fun with class loaders previously, and I'm actually going to run the demos on that as Anton speaks. So I'll be part of the VJug group that actually do some presenting for a change. Let me unshare my screen. So all I've left to say is thanks again, Norman. If you could join us in IRC just to finish off a few questions that we didn't get around to. For anyone who wants to see this session again, it's available on YouTube at the same URL that you're watching it now on. So just refresh that. That should be available just a few moments after this connection is completed. So thank you, Norman, and hope to see you soon at a conference.
Thanks again. It was a lot of fun. And
great. Awesome. Thanks very much. Bye.